Well, good afternoon, everyone. So, let us continue to know about the trees today. So, we will mainly discuss about the binary trees. So, the different types of binary trees we have. Then, we will discuss about the tree traversal techniques. So, how we can traverse through the trees here, through the means how we can traverse, visit all the nodes in the trees. So there are three different types of techniques are there where we can use uh, mm, to visit the nodes in the trees. So we will discuss that also. So, so if I talk about the one last class, we discussed about the trees, different types of trees we have. Then we discussed means we mainly focused that tree is something a graph which is not having any circuit or a cycle. Uh, then we discussed about the various properties of the trees. Okay, then we have the tree terminology where we discuss about what is parent, child, siblings, degree, internal nodes, leaf nodes, levels, height, depth, subtree, forest, root, and edge. We have discussed. So some definitions, just let us recall them because those are very important for us. So the degree of the node is the total number of degree of the node is the total number of children of that node. So what is the total number of node children a particular node has? Then it is called the degree of the node, and the degree of a tree is the highest degree of the node among all the nodes. Means though some of the nodes may having only one child, some of the nodes may have two child or three or more. So the largest one will be become the degree of the node. Then we have the internal nodes, which is not a leaf node. That's the leaf node which has no childs. Then we have the level. So the level, the root node is always at zero. Then we have at level 1, level 2, and level 3 nodes. Then we have the height is the total number of edges that lies on the longest path from any leaf node to a particular node. So the height of the tree uh, is the height of the root node. So the height of the root node means from the bottom to the top, how many number of edges if you count, then we can say it is the height. Now here the height of the tree is actually 3. The height of mm, the height of the tree is 3. So the last level, whatever will be the last level, that will be the height of the tree. That is a simple way to remember. And the total number of depth is the total number of edges from the root node to a particular node. So from root node to the particular node, the total number of edges we have means that also from root node to the particular node. So 1, 2, that is called as the depth of the tree. Uh, the reverse of the height. Okay. Then we discussed about the subtrees also, then the forest we had discussed. Next, we started our discussion about the binary trees. What actually is a binary tree? Okay, a tree with only two, at most two nodes, called as a binary tree. Means either it can have a zero child or one child or two child. Such a tree is called as a binary tree. Okay, and if you observe that in this particular tree, we have nodes with one child or two child and zero childs also. Okay, and then we discuss about the unlabeled binary trees uh, where you can form 2 power n cn by n plus 1 on different kinds of binary trees. Okay, then we have seen all those all forms here. Okay, if suppose if you take the number of unlabeled nodes as 3, then it is 2 into 2c3 means that is 63 by 4. That is 5 different types of combinations we can form. 5 different kinds of binary trees you can form. Then you have the labeled binary tree. So where we can have the labels here. The number of different binary trees possible with n labeled nodes is 2 n cn by n plus 1 into n factorial. So if suppose it is 3, so we have 5 into n factorial, that is 3 factor 6, 30 different kinds of labeled binary trees are possible. And for each combination we have 6. That is, if suppose ABC is taken, so we have ABC, then BAC, then CAB, like that we can form different types of nodes. Then up to here we have discussed already in the previous class. Now let us continue and let us learn, let us know some new things today, that is about the various types of binary trees. We have the rooted binary tree, we have the fully or strictly binary tree, then we have a complete or perfect binary tree, then we have a skewed binary tree, then we have almost complete binary tree. So rooted binary tree, if you can say, rooted binary tree is a binary tree that satisfies the following two properties. So when you can call a binary tree as a rooted binary tree, you can call it as a rooted binary tree when it has a root and each node has at most 2 children. So each node it has 2 children, then it is called as a rooted binary tree. Means at most 2 children means you can have 0 children or 1 children or 2 children. At most has at most 2 children, then it is called as an rooted binary tree. Okay. Then you have full binary tree or strictly binary tree. So a binary tree in which every node has either 0 or 2 children is called as a fully binary tree. So here it can have fully binary tree or strictly binary tree where each node can have 0 or 2 children. Means compulsorily it should have 0 or 2 children. It is mandatory. And for example, if you see, observe here, so you have A, B, C, means B, C, and C. For C, it is having only 1 child, so it is not a strictly binary tree or fully binary tree. Whereas in case of this tree here, so it has A and 2 children, then B has 2 children, then E has 2 children. Means either 0 children or 2 children. It should not have 1 children there. So such a binary tree is called as an full or strictly binary tree. Then you have complete or perfect binary tree. A complete or perfect binary tree will have 2 properties. Every internal node has exactly 2 children and all the leaf nodes are at the same level. So every internal node will have 2 children and all the leaf nodes will be on the same level. So here C is a leaf node. C is a leaf node and D and E are the leaf nodes. So D, E and C are not at the same level. C is at level 1 and D are at level 2. Right. So whereas in case of this perfect binary tree, the second one, where you can observe, where you can see that, so B and C are at one level and all the leaf nodes D, E, F, G are at the same level, then it is called as an perfect binary tree. And every internal node is having also 2 children. So C is not having 2 children. It is an internal node which is not having 2 children. Okay. Then you have almost complete binary tree. What is this almost complete binary tree? So it is a binary tree that satisfies again 2 properties. All the levels are completely filled except possibly the last level. Means all the levels are completely filled, and the last level must be strictly filled from left to right. Means it should be from left to right, should filled. Like means from A left and right, then for B, D, E, and F. So this the one which has been crossed is not an almost complete binary tree. The reason behind why it is not complete binary tree here is here after filling D and D to means the child nodes for B, for C, F should come to the left side, but it is coming for the right side. So that's the reason why it is not almost binary tree. So whereas here see F is coming at the left side, such a node is called as such a tree is called as an full almost binary tree here, almost complete binary tree. Then you have a skewed binary tree. What is a skewed binary tree? Which is again having 2 properties. All the nodes except the one node has one and only one child. Means all the nodes except one node has one and only one child. The remaining node has two child. So see, the remaining nodes has no child. Means every node here is having only one children. All the nodes except one node has one and only one child. The last node is having no children. That's the point. Except one node, all are having only one child, and that remaining node has no child. So one child is there. So such a binary tree is called a skewed binary tree, and the skewed binary tree of n nodes such that its depth is n minus 1. Its depth is n means see 1, 2, 3. So its depth is n minus 1 there. So three edges are there. So it is a left skewed tree because all the nodes are in left side, and it is a right skewed tree because all the nodes on the right side. So there you can have one left, one right, one left, one right also. It is also a skewed binary tree, but if all the nodes are at only left side, then it is called as a left skewed binary tree. If all the nodes are on the right side, then it is called as a right skewed binary tree. Okay, so these are all the various kinds of binary trees we have. Okay, so the definition. So if you practice once or twice, it will be helpful for you, because by seeing the diagram itself, you can simply identify whether it is a rooted binary tree or a full or strictly binary tree, complete or perfect binary tree, almost complete binary tree, or skewed binary tree. Okay, so you need to have the idea about these the particular nodes. Then you have the binary tree traversal. Binary tree traversal. Sorry, binary tree properties. Let us talk about some properties of binary tree. So the binary tree properties are the first one is a minimum number of nodes in a binary tree of height h will be h plus 1. So the minimum number of nodes, minimum, it is minimum number of nodes, a binary tree of height h will be h plus 1. For example, to construct a binary tree of h height 4, we need at least 5 nodes. We need to have 5 nodes. Of course, it is left skewed binary tree, see here. So of height 4, we require 5 nodes to construct it like this. Okay. Then the property 2 is maximum number of nodes in a binary tree of height h will be 2 power h plus 1 minus 1. Okay. The maximum number of nodes a binary tree of height h will be 2 power h plus 1. So for example, here with the maximum number of nodes of a binary tree of height 3, if it is of height 3, then 2 power 3 plus 1, that is 16 minutes. So you should have 15 nodes. We must have 15 nodes here. Okay, so thus the binary tree of height 3, the maximum number of nodes will be 15. So see here, 15 nodes will be there. A, B, C, the height is 3. So 1, 2, 3. Okay. Height is 3. From the leaf node to the root node, we are having only 3 edges at a maximum. So it is an height is 3, and we can have it can possess maximum of 15 nodes, not more than 15. And we cannot insert more number of nodes in this binary tree. So if you observe that, you cannot. So if I insert any node, so either it should insert all the leaf nodes, then the height of the tree will become 4. Okay, so that's the formula. You need to remember that if the maximum number of nodes of binary tree of height h will be 2 power h plus 1. Okay, then the next property is the total number of leaf nodes in the binary tree is equal to the total number of nodes with 2 children plus 1. The total number of leaf nodes in a binary tree will be the total number of nodes with 2 children plus 1. Total number of, okay, nodes with 2 children plus 1. So for example, so total number of nodes with 2 children. So how many nodes are there with 2 children? A is having 2 children, B is having 2 children. Okay, so 1 2 and plus 1 3. So 3. So one, G is one leaf node, E is one leaf node, F is one leaf node. So that's the formula is satisfied. So again I repeat here that the total number of leaf nodes means of a binary tree is total number of nodes with 2 children plus 1. So here A is a node which is having 2 children. So one node, B is a node which having 2 children, that is 2 nodes. Sorry, 2. So the count is 2 plus 1 is 3. So it should have 3 leaf nodes now. So let us check whether it is having 3 leaf nodes or not. So G is a leaf node, E is a leaf node, and F is a leaf node. Okay. Next, property 4 is see another node. It is given here that the number of leaf nodes in a binary tree depends only upon the number of nodes with the 2 children. So how many nodes having 2 children? It depends upon that. So accordingly, you can find the number of nodes with 2 children. Okay. Next, we have property 4. The maximum number of nodes at any level L in a binary tree is 2 power L. The total number of nodes at any level L will be 2 power L. If you know that root node will be at level 0, then 2 power 0 is 1. So there will be only one node. Then at level 1, okay, level 1, 2 power 1, 2 nodes you can have. Then you have at level 2, 2 square, 4 nodes. So if you observe this, this particular tree, so at 0, 1, next level 1, you have 2 nodes. Then level 2, 4. And third level is 8, 2 cube is 8. So 1, 2, 3, 4, 5, 6, 7, 8. So that's what the definition states here, that total number of nodes at any level will be 2 power L. Okay. Some of the problems are given. So just I will share this particular link. Just go through and see what problems are given there. Next, the tree traversal techniques we have. The tree traversal refers to the process of visiting each node in the tree. The tree travels means how to visit all the nodes in the tree is actually called as a tree traversal. The tree traversal can be done in 3 ways. So there are 3 ways. So one is pre-order traversal, in-order traversal, and post-order traversal. So we have depth first traversal, which is pre-order traversal, in-order traversal, and post-order traversal. That is called as a depth first traversal. Then you have the breadth first traversal also. So in these 3 techniques, okay, pre-order traversal, visit the root node, traverse to the left subtree, call pre-order of left subtree, then travel the right subtree, call the pre-order of the right subtree. So it is an recursive algorithm here. See, first you need to visit the root node, then you should call again the pre-order, call the pre-order of left subtree, then you should call the pre-order of right subtree. Okay, means root, left, right. Root, left, right. For example, see here, now this is a tree. So visit, now this is an entire tree here. So according to the algorithm, it is said that visit the root node. So what is the root node? A. Then you go for, then it said that traverse to the left subtree. Now this is the left subtree here. B, D, E is the left subtree. Now consider this as an again separate tree. Separate tree. So then again, what is the root node? B. What is the root node? B. So it should be. So next comes B. Then again go for the left subtree, D. So what is the root node here? D. There is no left, there is no right. So A, B, D. Then comes, so for B, already left side is completed, then you go for right side. So A, B, after that E. Then you have again go back. So A's left side is over, then again come to the right side. Then in the right side, you take it as a right subtree. Then again, for the right subtree, visit the root node. Root node is C. Then again, you come to the left side. So for the left side, F is the root node. F is visited. There is no left. There is no right. Again, you go back to C. Its left is completed. Then you come to G. So G is the root node. G is visited. So there is no left. There is no right. Then you go to C. It is over. Both root node is visited. F is visited. G is visited. Then you go to this one. So entire algorithm is completed. So I repeat it once again. Just observe it very carefully. Observe it carefully. So it states here that first you need to visit the root node, then you have to traverse to the left subtree, means recursively call the algorithm. Then after that you recursively call the right subtree. So first I am visiting the root node. Here the root node is A. So I have visited A. Now for A, I have to go for left side and I have to go for the right side. Now first I am going to the left side. In left side again, this BD is a subtree. So I have visited the root node B. Then I go to the left side. Okay, D. For again, D is a subtree. D is visited, root node is visited. There is no left subtree, there is no right subtree. Again, come back to B. For B, root is completed. Then left is also completed. Then you come to right side. For E is the root node. E is visited. There is no left, there is no right. Then you can come back to B. So B's root is visited, B's left side is visited, B's right side is visited. Now come back to A. So A is already visited first, its left side is completely done. Then you come to the right side. After coming to the right side, you visit the C. Okay, you visit the C, and then you have root node is visited. Then you go to the left side. Then again for F, this is the root. F is visited. Then no left, no right. Again come back to C. So C's root is visited. Left is also over. Then come to the right side. G is visited. So we have A, B, D, E, F, E, C, F, G. So it's an way you're supposed to visit the nodes. So there is a shortcut for that. See here, the traversing the entire tree starting from the root node will be like this. See this. This is very simple way of visiting. You start from the root. It's just to draw a line like this from A to B, then to D, then to E, then again coming to F. Sorry, C, F, G, and you go back to A, N. So no need of means in exams sometimes it is given tree and they may ask you to write the pre-order, in order, and post-order, or otherwise in an interview also they may ask you. This is the easy way to remember. Just you can draw the line to any tree, and then you can get the pre-order traversal of that. So likewise, if I go to see this, what is the pre-order traversal of this one? Simply A, B, C, D. That's it. Here also A, B, C, D. So if you draw a line, it will be like that. Now for the pre-order traversal of this one is A, B, D, E, then again C, F. Okay. Simply if you going on drawing the line, that will be the pre-order traversal. So for this one, A, B, D, then E, then C, then F, and then G. Okay, like that you can take any tree for this one. A, B, D, E, F, G. Again you come to C and H. For this one, A, B, D, E, F, G, and to C. So this is how you can traverse through the entire traversing technique here. Okay. The applications of preorder traversal is used to get the prefix expression of an expression tree. So if some expression tree is given, so to get a prefix expression of an expression tree, you can simply get using the preorder traversal. And it is also used to create a copy of a tree. So if you want to create a copy of a tree also, you can go for the preorder traversal. Next we have the in-order traversal. The in-order traversal will be like this. First, visit the left subtree called the in-order, means you have to go to the extreme left. Then after that, you have to visit the root. Then you have to come to the right subtree by calling the in-order traversal right subtree. So previously it is root left right. Now it is left right and root, means go to the extreme left. Yeah. So for example, if you go to this one, go to this one, A. A is a root node, but what is the first statement here? Go to the left subtree. So going to the left subtree. Again for B also we are having left subtree. So for D, go to D. Means from A to the left you are coming to D. So for D there is no left. For D there is no left. Now you are visiting the root. So you are visiting them. For this particular subtree, you are visiting the root. And for D there is no right subtree. Right. So D comes first. Then after that go back to B. So for B left is completed. Now the root. So B is the root. So B is visited. Then E. So D, B, E. D, B, E. Now you come to A. So A left is completed. Okay. So once again I repeat. So according to the algorithm here, you have to go to the extreme left, then the root and the right. So first to the left you are going, again you are having left, you are going to left. So there is no left, then you are visiting the root, then there is no right. After then coming here, so you have went for already left there, then you are visiting root B, then you are going to right. So once you are going to right, so E, for E there is no left, so E is visited. Then for E there is no right. So you are having D, B, E. Then you come to A. So for A left side is completed. Now you are visiting A here. Okay. Now you are visiting A. Okay. Then after that you are coming to C. For C again you are having left. So go to left. For F, there is no left subtree. Then you are visiting F. Then there is no right. Okay. Then after this completion of this, now you come to C, and then from C, after visiting the root, you come to the right side. For G there is no left, so visit the root G, then right. So that's the reason why we have D, B, E, A, F, C, G. So this is how you need to traverse. Okay. So here again the shortcut is given. See here. To draw the lines. So first D, then B, then E, then A, F, C, and G. This is the easy way to construct the in-order traversal. So what are the applications? In-order traversal is used to get the infix expression of an expression tree. So if you want to get an infix expression of an expression tree, then you can go for the in-order traversal. Then you have the post-order traversal. So in the post-order traversal, we have the traverse the left subtree. First you have to go to the left subtree, then you have to go to the right subtree, then root. Now this time left, right, and root. Traverse to the left side, then traverse to the right side, then visit the root. So what is that? Now for this again, see, for A left side, again this is a subtree. For BD, so again for B left side. For D, left side, there is no left side. For D, there is no right side. Now visit the route. So D comes first. After visiting D, to go back to B there. For B, left side is completed. For B, you have to go to the right side. Then you are coming to the right side. For E, there is no left side, there is no right side, then E. So first D is visited, then E is visited. So again go back to B. So for B, left is completed, right is completed. Now visit the route. Now you are visiting B. So D, E, B. Go to A. So A, left side is completed. For A, left side is completed. Now go to the right side. According to the algorithm, you have to go to the right side. You should not visit the root node here. So go to the right side. For again this subtree CFG, okay, again go to the left side. After coming to the left side, for F there is no left, there is no right. So F is visited. After visiting F, you come to the root node. So because root node is not visited, you have to go to the right side first. So go to the right side. For G, there is no left, there is no right. So after F, it comes to G, then C, okay, the root node, then come to A, because A's left side is completed, A's right side is completed, then you are coming back to A. So the answer will be D, E, B, F, G, C, A. D, E, B, F, G, C, A. This is D, E, B, F, G, C, A. This is how you are going to visit the post order traversal. So it says the shortcut for here, pluck all the left post leaf nodes one by one. Okay, D is plucked. Okay, then after that E is plucked, then B, then again for F, after plucking left side, then again G, then C, and then E. Okay, so this is how we are going to traverse. So if you take one or two, three trees, if you can practice, then it will be helpful for you. So this post order traversal is used to get a postfix expression of an expression tree in general. Okay, so this is used to delete a tree. So if you want to delete a tree, then you can go for this post traversal using delete tree. Okay, and this is because deletes the children first, then deletes the parents. So because why it is used for deletion is because it deletes the children first, then it will delete the parent. Okay, so those are about the depth first search. Then you have the breadth first traversal. Breadth first traversal of a tree prints all the nodes of a tree level by level. So here breadth first search traversal will print all the nodes level by level. So it is also level order traversal. It is also called as a level order traversal. Means you'll have F, sorry, A, then you have B, C, then you have D, E, F, G. A, B, C, D, E, F, G. So level order traversal is used to print the data in the same order as sorted in the array representation of a complete binary tree. So what is the application of this? The level order traversal is generally used to print the data in the same order as stored in the array representation of a complete binary tree. So if you want to have array representation of a complete binary tree, so it will be displayed in the same order. So that is about the traversal also. So here some examples are given. Okay, so you can go through these examples. You can just see how we can print the traversal. So means how we can print the get the solutions. Okay, so that's it. We will conclude it today. So any doubts regarding this?
No, sir.
I will share that web link also. So just go through it, and if you can have any doubts, you can ask me in the next class. Okay.
Okay, sir. Thank you, sir.
Well,